Welcome everyone. The purpose of this video is to take you through some of the steps associated with the spatial applications for this week. So in general, the spatial applications are designed to help give you a little bit more of an appreciation of how to build, design, or a workflow from our goal back to our parent data sources and understand how to build, I think of it as a network diagram of steps and data that we'll need to create in order to solve some problems. This really builds upon some of the other videos that are posted for this week as well. So with that, if you are able to pull up what you see on your screen for this week, this is the Spatial Analyst Applications document or guide, and the purpose is to show applications with spatial modeling. And with that, we'll be going through a few small samples here of government disaster and insurance planning, natural resources, and business. So with that, you will want to copy the spatial part 1 folder, and that is currently under week 2, at least at the time of this video here. And so with that, let's go ahead and take a look at the first application. So with that, as before we get into the case study itself, you may want to open up your Arc Pro session. Just a new session is fine for that. So before we get into the case study here, I just wanted to show you what this folder looks like, and you'll need to download this folder here, Spatial Part 1, that is provided in this week's materials as a zip file. So you'll want to download that by right-clicking and downloading, of course, and then once it's saved, right-click and extract all. So you'll extract all those files to a directory of your choice, and then also please make sure there are no spaces in your directory and your path name. Once that is set up, feel free to go ahead and open up some data or open up the folder and explore the data sets in here. All right, let's come back to our spatial applications workshop. So with this, go ahead and take a look at the short overview. This one happens to deal with government planning and insurance applications. Namely, we're going to be working with a couple simplistic data sets for this one, that being a land use raster and a flood zone raster. And our goal is to identify the residential parcels that fall within a flood zone. So relatively straightforward, but still they'll build upon our understanding of how we are working through subsetting values, and learning a little bit more about condition statements and how to write those. All right, so in general, pretty easy, understanding values and subsetting in our rasters. Okay, so with that, let's go ahead and start with step 1, which is to load the flood raster and land use raster to your map within the Spatial Part 1 folder. And our map units are in feet. So let's add those. So I'm going to add my flood and land use. And hopefully those add for us. But the flood and land use rasters. And then we'll turn on the flood zone layer and notice that those areas of the flood zone where it affects the different land use areas. So once that loads, let's go ahead and explore our data in here a little bit. I'm going to right click and zoom to layer just to bring everything into perspective, because the initial base maps are not obviously in the same coordinate system. And this is, I think, undefined coordinate system here, but the units are in feet. I'm going to move my flood raster on top and maybe change the color. Just left click on my value of 2. And the color's not too far off, but let's give it a little bit different of a color of water maybe here. And some of our vacant land isn't exactly ideal for color schemes, but it's okay. Now feel free to zoom in, and I like to sometimes just turn on and off these layers. And this is an application that's oftentimes used for not only insurance, but different ordinances that states or counties, probably more so counties, might have about flood zone ordinance, or flood zone ordinances that regulate what you can do inside of a flood zone, such as build homes, put up septic systems, things like that. So this is a real, somewhat of a real application. And in the past, I've had to encounter, different codes for building offsets and using elevations that delineate a flood zone for either a 100-year or 500-year flood, and how you may need to obtain variances in order to build within these regions, or different types of preventive protocol that you'll need to do, if you're building a home or purchasing a home, dealing with flood insurance and whatnot. So a lot of times companies will use those high water marks or high water elevations for a 500-year, 100-year flood event. And those have been happening a lot more frequently as of late. So definitely something that people look at. Occasionally these are revised with new elevations and new surveys, but something, just to throw in there that is a real thing to be mindful of here as we're going through that. All right, so after you've had a chance to explore your data, we know that our flood zone raster here has values of 2. And we also see our land use raster has a series of different user-defined attributes in our attribute table, or VAT here. But more importantly, we're going to pay attention to the value. What's the value? What's the meaning? And the value, for instance, here, 3 is value of 3 means residential. And that's what this exercise happens to be dealing with, is looking at the number of residential areas or parcels that fall inside of a flood zone. So if we identify our values of 3, that tells us that those would be falling within a value of 2, which is our flood zone here. And that's the idea ultimately with this exercise. So step 1B, we're going to define the locations of the residential areas within the flood zone. And here's an opportunity for us to think about how we want to design our workflow. So we've explored and identified residential areas already. And now where are they located inside of that flood zone? So let's build a little bit more of a detailed analysis here. All right. So with that being said, think about this and how it may work for you. I'm just going to pause the recording and pull up a note sheet for me here, and then we'll be right back with you so I can help you design this on the DocCam. Okay, so with our flowchart, I'm going to give you a couple of different scenarios that you may think about in this application. And with that being said, like before with some of the other videos posted this week, let's take a look at our goal. And so we're going to work from a backwards design principle. What are we trying to identify here? We're really looking for what we'll call wet homes or wet residence areas, areas that are of residential designation that fall within the floodplain. So that's that is the goal for us here. And the question for us now, like you may have seen in the other videos this week, is to say, how are we going to do that? So we know that there is an analysis that will take place here. We just do not know exactly what that is yet. But we do know that we have a flood zone raster here, and we know that the value of those cells in that raster are 2, values of 2. We also know here that we are looking for our residential areas from our land use. So we know that, and there's a couple ways to do this. I'm going to show you the broken down way first. But we know that we're looking for wet homes. And if we explored our data over here, we know that we did that before here, that our residential areas are values of 3. inside of our land use. But let's say we want to pull out the residential parcels. This is a raster for us. And I'm going to, we know in the original data set, the residential parcels consist of a value of 3. However, if we subset that out, we'll call them maybe values of 1 for right now in this example. So that tells us, well, we know the residential areas ultimately come from our land use. Our land use raster. So what are we getting to? Here's our goal. And then here would be our parent data sources. And in these exercises, that's all defined for us, so that's pretty easy. But in a sense where if we're not sure what these are, the idea is we're working this way. We're working this way to identify what our parent data sources are. This just happens to be scaffolded out a little bit for you so that some of the work's been done in terms of isolating the parent data, but working on this design should help us think about what we may want to do. Okay, we know that one of our layers, our flood zones, are ready to go. Let's go ahead and take a look at our land use raster. And what we are going to do right here will be to what we've introduced in other videos. We'll call that subsetting data. Or another way of thinking about it is data derivation. This is probably more of a subset, but when I say data derivation, that means let's add an elevation raster. And I wanted to derive an aspect raster from that. An aspect raster would be derived from an elevation raster. So that would be more or less, I would call it a more appropriate term for data derivation in this case. So we'll maybe call this a subsetting. So we're going to be, or grid query. That's what the word I was looking for, grid or raster query. Raster query. So it just means like you would in a vector data set, you're just setting up a query of your attributes. That's kind of what this is doing. We're going to pull out values of 3 that we know were residential. We're going to call them 1. Just for the, I mean, we can call it whatever we want it, but we'll just call it 1. And that will set up for us here an analysis that we can delineate out here in just a moment. But let's go ahead and subset that out. All right. So a lot of ways we can do that. And I'm going to go ahead and go under my toolboxes, scroll down here to our Spatial Analyst tools, our map algebra, and then Raster Calculate. So I'm going to go ahead and use our good old condition equation, and I'm going to type in there land use, and we'll find our evaluator. Remember, we're going to use our test for equality where it's tested and evaluated. We don't need that comma right there. Tested and evaluated for 3 because that means residential. We'll go ahead and add another parenthesis up here because we know we're going to need one. Where that is true, let's write a 1. Where it isn't, let's write a 0. Because that's what we're going to end up with right here. We're going to have values of 1 and 0. So 1 being the true, 0 being our false. Okay. So on the condition where land use is tested and evaluated for 3, which means all of these red colored areas right here, where all of those are true. In other words, where they're residential, let's pull those out. We're going to query or subset that out and call them values of 1. Everything else will be 0. And we'll call that, we'll develop a new raster here. I'm going to make sure again I'm in my working directory. So your directory may be a little bit different from mine, and that's okay. I'm going to call mine, even though my folder's here, I don't want to, I'm not going to work in there. I'm just going to work at the level above it here. I'm going to call this one res, or residential. So here we go. We have our path name, no spaces. Let's go ahead and run that. Okay, very good. Parameters executed, and that is fine. So here we have our values of 0 and 1. And just for the sake of our discussion, I'm going to left click on my value of 0 and just set that to no color, just so I can see through it. That's all. Now I'm going to turn off my land use. We no longer will need that. And I'm going to turn on my flood zone. And now here you can see the affected parcels. So you can kind of say, well, yeah, I mean, here we are. We have our residential parcels that we see are falling within our flood zone. And that really takes us to our stage, right here. We have our flood zone raster. We have our ResRaster. Now let's integrate this. And so a couple of ways you could think about doing this. One would be multiplying them. We would be dealing with, if you think about like, what would my values be if I were to multiply this? Based on some of the other videos, if we were multiplying, I just kind of sketched this up here. Kind of small. So I have 1 and 1, 0 and 0, and then I have all 2's down here. So I make my output a little bit larger. If we were to multiply those together, we would have 1 times 2 would be 2. That would have been a residential plus a flood zone. So that would have been okay. And then we'd have 0 times 2, which is obviously 0. And then we would have 1 times 2. And then 0 and 2 again. So the 2's would be our flood zones. If we did this approach, if we multiplied those. Another way to do that is to write a condition statement. That way we can enforce and control our output. So let's say we wanted our wet homes, our final raster. This is a raster output. Let's say that we wanted these to be in 1s and 0 for a true and false parameter. Then I would go with the condition statement. So our condition statement would be on the condition where the flood zone is tested and evaluated for 2, and where the ResRaster is tested and evaluated for 1. Where those conditions are true, then let's write a true value of 1 and a false value of 0. That will give us a wet homes raster that just showed the residential parcels by themselves. So let's try that. So we'll call this one wet homes. And I'm just looking off of our sheet right here. We're going to query the land use layer to create a new layer containing residential areas. And then obviously we have our flood zone, and then we'll process this to get our wet homes or something else that we want to call that. And you can generate stats of this or the area and square footage. We've done that in some other videos. It's just our area of our cell size times our count. So you can do that if you want to. But let's come over here and I'm going to leave most of our work here intact, just so I don't have to retype all this in. And we'll call this one where our flood zone is tested and evaluated for 2. We know that all of our values, or all the cells in our flood raster, contain a value of 2. Where that is true, and then we're going to say, and take out an extra space here, new parenthesis, and where res is tested and evaluated with our test for equality, or 1, where those are true, we'll write a 1, and where it's not, write a 0. I don't know why that mark always shows up in there, but on the condition where flood zone is tested and evaluated for values of 2, and where res is tested and evaluated for values of 1. So flood zone 2, the residential 1, where those are true, we'll write a 1, where it's not, write a 0. So our parentheses all are checking out for order of operations. We're calling it wet homes. Let's try it. Okay, I'm going to turn off everything else that I have. And that shows me the wet homes. So we're just dealing with only those values. So if I, again, wanted to turn off my, or not turn it off, but just set that to no color, I'm left with all my residential homes. So that is one way to go about solving this problem. I do have up here a word solution guide in this week's material that I propose a number of different ways that you can solve this. And I like using the con statement rather than just, taking land use, test and evaluate it for 3. But I encourage you to try all of these steps. And the one we just used, we first use land use, test and evaluate it for 3 to pull out our res parcel. And then here with some of the different analysis steps. A couple of different ways that you could code those in. Again, personally, I like the condition because it steps you through thinking logically about what's going on. Step 2 up here is kind of doing the same thing for you with the implied notion of a grid query, if you will. And we talked about multiplying those. I mean, you could even add those as well. What would your values be if you added those? We had 2s and 1s in our case, so your output could be 3. 3s would be, of course, our flood zone area. And then there's what I call the bypass method. And I want to talk about that in some of the other videos. I alluded to that. The bypass method is definitely applicable in this case. And what that means is that, and you may have caught this already too, saying, okay, I know my values in my flood zone are 2. I know that in my land use raster, my residential parcels are tested and evaluated for 3. So why do I need to subset that out? In short, you really don't need to subset this out. Sometimes I like to recommend that just for the fact that it allows you to get more practice and breaking things down, looking at things more clearly. But what that bypass method would do is essentially says, okay, with a condition, I'm going to still pull out these values of 2, but instead of breaking this down from a subset or a grid query to pull out the residential parcels, I'm going to go to land use. I'm going to say land use where that's tested and evaluated for values of 3, because our residential parcels in that original layer contained a value of 3. Therefore, your condition statement would read, for the flood zones 2 and the land use raster is 3. Where both of these conditions are true, let's write a 1 for an output and a 0 if it's false. So that's what this bypass method is saying. We're kind of bypassing this step right here. So you do not need to necessarily do that. So something you can try and explore and think about. Breaking things down. The reason to break them down is that you can try to use a little bit more of the multiplication or addition. And in this case, it really wouldn't matter a whole lot if you multiplied or added, but by breaking it down, that residential parcel will allow you to make a little more sense if you were to multiply or add the flood zone and the residential parcel. So that is a reason to break it down. When I say break it down, I'm referring to adding in this step, breaking down the land use raster into something that just contains 2 values. Because in our original land use raster, I think there were like 7 or 8 values. So breaking that down, it gives us a little more control that now we're only dealing with, several different values here, 3 altogether, 1s and 0 and a 2. And how we add, multiply, that's what gives it the flexibility if you were to break that down. So that is a good reason too, if you were wondering about that. Okay, let's take a look at the next application. And let's pull that one up. This is what's called a resource conservation application. And pull my notes up here. And once again, we'll have an opportunity to build a flow chart for this one. So it's another good application. And in this instance, we'll be helping the landowner balance pH levels in a field for the next growing season. So I think a lot of this with precision agriculture and understanding, when somebody's out, conducting soil samples or precision ag, and you're calibrating the GPS on the fertilizer or the spreader, you're balancing a more predictive amount of fertilizer for what the soil actually needs. There's an instance when I worked in county government, I was calibrating manure spreaders. It was a dirty job, man, but it was kind of fun to do that. And what it entailed was taking out these great big huge scales. Like you drive the spreader onto it, and I'd take the weight, an empty weight and then a loaded weight, and then the producer would go to the field and spread the fertilizer, manure, whatnot out onto the fields, and I would take the windrow of that, usually in the winter. It was a little bit easier to see, but I'd measure the windrow. In other words, how wide the windrow was, and then how long it was, and then calculate all that together with the weight that was applied. And basically, what you end up with is a amount of application per ton per acre. And there were a couple of instances where I remember, man, this one person, he was putting on, I think it was like 100 times what the ground could hold. And that's where we develop nutrient management plans and being more effective at what we have, or when anybody has different fertilizers they have to spread, or dealing with smart growth and 1,000 cow dairies, you have to have the land to make sure that stuff can get spread out on. Otherwise, we're overloading the nutrient loads for the ground. Either it runs off, or it's too much for what it can handle, and just debilitates trout streams and water tables and all sorts of problems with nitrates and things like that. So this is a neat application with that, of saying, what are some ways that we can incorporate, little GIS methods, spatial interpolations, to understand, here we're dealing with pH, but we could really analyze anything so long as we have some input data to look at with that. So take a look at the overall case study here, if you will. And this one is a little bit more straightforward, not a whole lot of craziness in here, but essentially we want to talk about the crops and having a balanced pH. 7 is a balanced pH level up here. And in areas in the field with a pH less than 7 are treated with lime, obviously, to help raise that pH. Lime is a little bit lower on the pH level. In areas with pH above 7 are treated with ammonium sulfate to lower the pH. So it's kind of acidic versus non-acidic, if you will. All right. So it says here the landowner should not treat an entire field with all lime or all ammonium sulfate, obviously, just from kind of the precision ag industry and being mindful of that. And so we want to locate areas of high and low pH and treat them accordingly. And so the farm size, I call it the field size is maybe more appropriate, is about 5.35 acres. And so we're going to help the landowner find the areas that should be treated with ammonium sulfate. So what we're looking for specifically, if we were to break down a goal for this, areas with greater than 7 pH. So that's our goal. Find areas in this 5.35 acre field that have pH values greater than 7, greater than or equal to 7. And so then we'll say greater than 7. 7 is neutral. So with that, let's go ahead and load in our two data layers here. We have the farm and we have a soil sample layer. So two layers. Let's open those up and check those out, and then go ahead and draw in your flow chart here. So I'm going to insert a new map for this application. Get rid of these. Do not want those. Again, our map units are in feet. Okay. All right, and what did I say there? We wanted the farm was 1, and soil sample for the soil samples would be the other. I'm going to change this one to the farm. That way we'll keep them separate from our other one that we did over here. That one was our wet homes. Keep them separate. Okay, now we'll have to zoom to layer, zoom to the farm. Okay, so here we have the farm. Again, our units are in feet here. And again, the coordinate system is not going to jive well with us just for the fact that those base maps are in a default coordinate system. And so whenever we zoom to a new data layer, that's going to try to project on the fly, if you will. And this can't really work because of our data definitions, but more on that to come in a few more weeks. So let's think about what we want to do. So explore our data. Let's look at the soil samples. So what in here stands out to you? You know, that's the question. We have a lot of good information, organic, biomass, potassium, phosphorus. What else do we have in here? Some of these I'm not sure of. We have an X coordinate, Y coordinate, and way at the very end, here we have a column on pH. So here we see some of the pH values for our different points. So this should be a little mental flag that goes off for you. Say, okay, what can I do with that? I know all these points. Now, first off, another question is, what do we have, vector data or raster data? Well, we know that our points here, and well, if we check on this, if we look at our properties, you know, if we go into our source here, spatial extent, this is a polygon, you know, so we know that we're dealing with two vector data sources. So interestingly, we do not have any raster data here. And so what can we do? We need to find pH values. And remember earlier in our discussions, we said vector data in terms of points are really, really good because we could generate raster data from it. So a light bulb should be going off to you and saying, what can I possibly do to get that pH down and maybe make a surface that is of pH that I could work with? So let's think about that though. Let's think about that. Let's think about that and build a little, whoops, how did that get on there? We don't need that on there. Okay. Okay, let's draw this in here, our flow chart. Square this up here for you here. So let's write our goal. What's our goal? Our goal is, you know, we want to identify all the areas that are, I'll call it greater than a pH of 7. You know, that's really the goal. You know, these pH treatment areas, that's kind of what we're looking for. So we'll call it, you know, some type of a, you know, like an ideal pH, you know, for these treatment areas. So we want to, after we explored our data, we know that we're dealing with two potential input sources, but let's think about that a little bit further. Where could we generate areas on our field right here that are greater than 7? We don't know what these areas are out here. We know what maybe this point is. We could say, oh, okay, well, gosh, if I click on this, it tells me that my pH is 5.8, but I don't know if that's really what I want to do. How are we going to do that? Give you a second to think about that. Maybe build it into your flowchart. So if you're thinking about, come back to our flowchart here. If you're thinking about, gosh, where can I generate, areas or pull out areas that are greater than pH? And we know that, after getting some experience, we may not know right now, but that's the whole point of doing these, is say, I can generate a pH surface. And if I have a pH surface, I know that I have to have an input to create a surface. So I could use my soil samples. Now this is vector, my shapefile in this case, a vector shapefile of soil samples. And what I'm going to do right here is say, okay, I am going to use the term that we referred to before, data derivation. So I'm going to derive data from my input soil sample vector shapefile. And data derivation, I'm going to derive a new surface that will be a raster containing pH values. And this is similar to if you had elevation points and you're developing an elevation raster from it. It's kind of the same thing, except we're just using soil samples and pH values. So we know that we're going to create a floating point. It's going to be a floating point. A floating point raster. And so let's go ahead and start here. We're again working our way back to the parent data and all the way to our goal. So we're kind of working this backwards. That's the idea. We start with our goal and ask ourselves, what would I need in order to achieve this goal? Where could I get pH greater than 7? Well, if I had a surface, I could isolate out those areas that are greater than 7. Okay, well, there's my surface. Now, where can I get my surface from? The light bulb's going on. Oh, yeah, in my soil samples, I had a pH column in there. I know that if I derive some data using called interpolation, I used an interpolation, like taking elevation points and interpolating the anticipated values between our known points to generate an elevation surface. I could do the same thing with soil samples here to get to pH surface. So let's try that. Let's take a look at our soil samples. We'll run something new called interpolation. And I don't know, we can use, I don't know that it really matters here. I'm going to just put in parentheses here. Spline interpolation, you might use a IDW as well. The IDW is going to give you a little more weight around your points. Spline is a little bit more useful for pollution concentration, water gradients, fertilizers, things like that. It's a little bit more forgiving and blending the surface a little bit more smoothing. So I'm going to use that. I'm going to use spline. Okay. Here we go. Let us go into our geoprocessing area here again, and under the map algebra we won't need yet, but let's go under I think we'll find that here. Where is under our interpolation. under the interpolation toolbar, or little toolbox here, and I'm going to select spline. Input point features. So we're going to deal with vector data here, our soil samp. Now our Z value, that's going to always be numeric. And what this is telling us is saying, okay, if you're going to create an output raster, you need to tell me, the software, saying, John, you need to tell me as the software algorithm here, what I need to do to compute numeric output for your raster. So what do you want that to be? And you all should be screaming pH. That's what we want for that one. So we're taking our pH value. So that Z value here in raster, when we're converting from or generating a new surface, deriving new data, always has to be based on a numeric value, in this case, pH for us. Output raster, I'm going to call this one pH. And output cell size, I'm just going to call, well, I'm not going to do anything yet here. Okay, I'm going to call this one cell size of 1. We know that our cell size, or not our cell size, our units are in feet. But if we know our units are in feet, and part of this problem is if we want to help the landowner figure out the total area that they need to treat, then there's nothing more beautiful than a 1 foot by 1 foot cell size. Easy to compute. If you have need to determine the area, well, 1 times 1 is 1. So set your cell size to 1. Always make your life easier in that regard if we have to calculate area in this manner. So let's go ahead and run this. I should mention actually here too, I might run this again. A couple things we may want to check out. Okay. This is a good illustration of something that's incomplete in our processing window right here. You'll notice that and this is something we'll want to change in environments, but we're missing part of our field right here, as you can see. So we're a little bit incomplete in here. We only extended our interpolated soil pH results to the extent of our sampling locations. And that's really not what we want. So we want to try to predict it to the edge of the field. So to that end, we're going to rerun this. I'm going to actually just remove this pH layer. We're going to run the same thing. I'm going to just call this one pH2. This time, everything else should be the same. But under environments, I'm going to set my processing extent right up here. Again, under my environments. And you can also do this under the analysis tab here too, under environments, either way. But processing extent, I want this to be the same as the farm. Same as the farm. Okay, so now if we run this, the interpolation will go out to the edge of the field. And you're probably saying, well, could it be more inaccurate if that's the case? Yeah. We don't have any predicted values out here, but we're trying to look at the entire field itself, just given the input parameters. So that's maybe a limitation of the data here, but nevertheless, we have a 5.35 acre field that we need to come up with some results for. So let's go ahead and go back to our parameters and run it again. Again, you have to give it a new name. Okay, now let's check it out. There we go. We have our pH values that now extend out to the extent of our field. And with that being said, at this point here, now we'll need to, we've created our pH surface. It's a floating point. So you can go check your VAT for that or your attribute table, and it will not show up for you as a floating point. And that's good. But now we need to do something really, our analysis is sort of taking place in here, but it's not really an analysis. I mean, it sort of is. But all we're really going to do now is take a look at all of our values in here. If we want to find out all these values that are above 7, which is pretty much this color range in here, those are the areas that we need to treat. So how can we pull that stuff out? In in our week session, we've been talking about relational operators and how cool they are to work with. And so with that in mind, I'm thinking something that if we just have really something of a data subset, or we'll call it a grid or raster query. We're just going to query out values, cell values from our surface that are greater than 7 to be treated. And then we'll calculate the area of that field and see how much savings we could make for the producer here in this case. So let's go ahead and try that. So let's back up to our raster calculator. And now we can say, I'm going to create a new raster called pH final. And I'm going to call that my pH layer. My pH 2 is actually what I have called mine because we recreated that to get to the extent of the field. So I'm just going to say pH 2, where this is, what do we want to say? Which one of these relational operators? Greater than, here, greater than 7. Well, that was part of our goal in all of this, is we're looking for the areas that are above 7, treated. And so once we have these areas, we'll try to find the area. We know that we have our cell size and 1 foot by 1 foot cell size. We'll be able to just take our area, which is 1, times our count, and then multiply it by, I think it was maybe on the next page, I think it was like $50 an acre or something like that, but at least in this example. But let's go ahead and run that. So our pH, taking this raster, we're saying I want you software to find all the cells that are greater than 7 and write them to a new raster called pH final. Let's run it. Okay. So here we have our pH final results, and like with some of the others, I'm just going to no color here my results, and then I can turn my farm layer on underneath that. And so here we have the purple areas in my case are raster data, and the farm is a vector layer, as well as the points are vector layer. But these would all be areas that are greater than 7 that we would want to treat for high pH. So let's flip over to the next page and see what else we have to do for this. So right here, we interpolated the surface of pH values from the samples, and we found the areas that with the pH greater than 7. So good work, we met our goal. And now what we'll have to do is, these are the areas that the landowner here now needs to treat to lower that pH back down to 7 in this case. So what you could do, if you wanted to, is determine those areas of that were greater than 7. Again, multiply the count. So if we went into the final pH here, looked at the attribute table, we said there were, well, in my case here, 18,747 times 1, we'd be dealing with 18,747 square feet. And if we multiplied the what was it here? I'm just looking at the assignment listing at $50 an acre here. So we could multiply, we'd have to convert our feet into acres and then multiply that value times 50, and that would give us the count to treat the application for ammonium sulfate. And what would also be cool, if you wanted to, you could take the entire acre. So you could take of the field 5.35 acres, multiply it by $50 an acre, and then calculate the difference, how much the landowner would save. Instead of doing the whole field, let's just look at the whatever was 18,747 feet, and we convert that to acres, which would be pretty small. And then multiplying that by 50, I mean, they could be saving a couple $100 just on that field alone. $50 is probably actually pretty cheap by today's standards, but for the idea here, I think you know where I'm going with that. But so give that a shot, and you might have something around $260 in total savings. You know, so I wouldn't expect the actual cost of treatment to this area to be very much at all, but nevertheless, it's the idea behind it, what we're getting to for this. So if you have any questions on this, give me a holler, let me know. Otherwise, let's take a look back here at the solution guide. So the resource conservation problem, what we worked through, number one, I kind of stepped you through building your design. And you can either use a spline or IDW, that's okay. And then we're using subsetting or grid query. You can do reclassification too, that would work as well. Didn't talk about that, but you could do that by just using the reclass under the one toolbar there, reclass tools. But this step here, subsetting, you know, working through this last bit here, the subset, this is really our analysis. You know, it's really more of just a kind of a query that we're doing. That's essentially what it was about there. So the other way we could do this, in our raster calculator, we just said pH is greater than 7, you know, or you could do this on the condition where pH is greater than 2, or I'm sorry, where the pH is greater than 7, we'll call that a 1, and where it's not, we can call it a 0. So a lot of different ways that you can do this one. You know, try a condition statement if you want. If you want to force an output to a 1 and 0, the relational approach has a default of 1 and 0 that we just noticed here as well. But it's just another way of going through and trying this. So try this multiple different ways. Use the solution guide that's out there, and that'll help you out in thinking through some things in a different way. Next, we're going to try the red lobster problem that we see next on the solution guide right here. So we'll get a chance to use a few of these here in our work overall, but we'll break these down and work through them carefully. And then again, there are multiple ways to do this one, kind of a complex bypass method and some other broken down versions. We might break them down and then run them with a condition statement. You know, the rest of them you can try on your own here too. So with that, let's go back to our pro session, and I'm going to insert a new map, and we will call this map here. I'm going to remove all of this. We do not need these in here. I always get hungry doing this project. Okay, under map, let's go ahead and add data. And I'm going to come back to our work along right here for our business application. So here we're going to examine Red Lobster locations and their customers to find a good location for opening a new Red Lobster. And so, you know, this is obviously not an ideal situation, just a brief run through to show you what we can do with distance and how we're dealing with proximity and customer density and things like that. But so there's obviously many, many more questions that should be answered if this thing were real. But again, it's another little example here of something you do for a final class project. You know, obviously it'd be perhaps a little more expanded than this, but nevertheless an idea. So let's go ahead and load in there our Red Lobster stores. Again, all these are point files, customers, and that is a typo, yes, but that is the way the original data, when the original data came in, it was called that. And then streets. So Red Lobster, customers, and streets from our Spatial Part 1 folder. Here's our customers, Red Lobster, and streets. Red Lobster, customer, streets. Load those in. Okay, we'll need to zoom to our layer here, not our attribute table, rather zoom to our layer. And then we'll get a chance here to check out all of our stores. But the Red Lobster, I'm going to change the symbology. Yeah, we'll make, there we go. I'm just going to make them a little bit different customers. We'll change that. Let's see if I can make these a little smaller. I don't think we need them quite so large. And the color, let's give them a dark color here. Okay, that helps. And our roads, you know, that's fine for now, our roads. We can see our customers. We can see our Red Lobster stores. So, you know, whether these are gas stations, Red Lobster, you know, it doesn't really matter. We're just showing you the purposes. Because yeah, I think in reality, we'd say, why would we need to put a fourth Red Lobster in the same area? We probably wouldn't even have three, to be honest with you, but it's for illustrative purposes. So, you know, gas stations or something like that might be more appropriate, or Caribou Coffee or something, Starbucks, whatever. Anyway, Red Lobster is what we have here. So we'll work through that. All right. So take a look at a few things. Where are the customers? Where are they spending the most money? Or who are the people that have the most money? So we're looking for, going through this looking for clues. So our Red Lobsters are customer streets. And okay, we pretty much have all of our layers turned on. That's okay. Doesn't matter. We'll be okay. So these are the parameters that we're given. If you had a chance to read the case study here for a bit, this helps right now. And so we're going to assume that any restaurants within a mile will compete for customers. I think that's in reality not probably the best, but you know, for now we'll just assume that. So we're going to say 5,280 feet. Again, units in here are in feet, but 5,280 feet or 1 mile of each other will compete for customers. So it's saying right now we need to stay away from that. We need to be within, or we need to be greater than 5,280 feet or 1 mile. And potential sites should be, oh, okay, well, that's what, yeah, sorry here. So potential sites should be more than 1 mile from any existing restaurants. And another thing we'll have to be thinking about, I don't remember where that was in here, it was consumer spending. So we're going to start by creating an analysis surface for distance from the restaurant. So we'll template that out. And we'll create a surface density representing consumer spending. You know, so one, we have the distance parameter, and then up above, where are the customers that are spending the most money? You know, and that's a good question. Maybe it wasn't explicitly called out here, but those are the two parameters that we're given. But let's, you know, first explore our data. You know, and one of the things is we look in our attribute table, we see here that we have an event and a location. Yeah, I mean, we don't necessarily need to know their addresses. We can see them on here, but spending is something that should jump out to you. Saying, okay, we don't know if this is dollars per month or annual, monthly, you know, whatever it is, presumably yearly, you know, if these customers have all visited a Red Lobster or something like that, you know, we don't really know. We're just taking it at face value here, but the spending column here is valuable because if we're going to create a density grid of our customers based on spending, again, we want a numeric value. This is going to be a Z field for us, Z value. That, again, always needs to be numeric. It cannot be text. Let's look at Red Lobster here as well. So really our Red Lobster, just store number 1, 2, 3. Okay, maybe not super helpful for us, but not a lot in there. Customers there is, and then of course streets. We explore that. Well, we have some of the street names, but nothing in our discussion calls of that. So how are we going to break this down? Let's go ahead and draw a flow chart. Let me get my document up. Then we'll talk about how to make a flow chart. Well, not how to make one, but how to make one for this application. So let's try that as we're thinking through how this can work out for us. The light is not helpful. Okay. So goal. We want to find, let's write our goal in here. We're looking for really the best, or we'll call it new red lobster. We want I guess the best locations for a new red lobster given the parameters identified above, which were greater than 1 mile away and had a relatively high spending density for our consumer input. So questions remain for us. Like, we don't really know what that spending density is. Like, what's a good threshold for that? And down below, they give us that information. You know, when it comes to a high spending density, in some of the other applications for this week, we had questions about that. You know, what does steep slope mean? What does high spending density mean? What does high income mean? These are all questions that you really need to have answered. We talked about referring to literature, referring to subject matter experts or SMEs, referring to white papers. You know, what is a standard acceptable value? Because if we change this value higher or lower, that could really change a lot of our analysis, a lot of our areas. So, but for now, we're going to use 0.2 and higher as a spending density, and we're just going to pretend that we obtained that value from some literature, I guess here might be the best way to do that. So we know right now that we're basically dealing with distance and spending density. So I'm going to come up here and kind of we know that there's going to be 2 ways in on these, or 2 kind of 2 channels coming in. We know right now that we need some type of a density raster here that contains values of spending density or high spending that's greater than 0.02, greater than or equal to, we'll say greater than or equal to, just based on this information down here. We're saying 0.02 or higher for our raster, we'll call it spending. And then we also know that we need to be, we'll have another raster of distance greater than or equal to 5,280 feet or 1 mile from away from another red lobster. So I'm thinking already in advance that if I have a raster here that shows just values greater than 5,280 and then not greater than, I know that my values pretty much are going to be 1s and 0s. Same thing with my spending density, 1s and 0s, 1 and a 0. So I'm looking already to create a binary, 2 binary rasters at the end that we can compare and analyze right here. Okay, so next question is, where can you obtain these final distance parameters? You know, recall these are criteria. If you remember back from some of our prior discussions, these are criteria. The criteria are final metrics for everything that we need. Now in our backwards design, it's really helpful when we have the criteria because it allows us to think about where can I obtain that from? So we're going to be kind of working this way. You know, in this backwards design, where can I generate all of these layers from? Where can I obtain those layers from? So from back to front, with the goal here of defining our parent data. You know, that's the ultimate objective. You know, we're sort of given that parent data now, so it's again a little bit easier, but always be thinking of what's my goal? What are my criteria that I'm going to need right before my goal? You know, so we don't really know 100% what our analysis is yet. How we're going to pull those together, we don't really know that yet, but we do know what our criteria are because they're spelled out. One here and then one here. So where could we obtain a distance raster from? Well, we could say, I know that if I had maybe distance to Red Lobster. And some of you might be thinking buffers too, but remember, buffers are going to give you a vector polygon. Not that you can't use those, but remember, rasters work better with rasters in the overlay. So I would encourage you to think about a raster, like a straight line Euclidean distance function, to develop a floating point distance to all red lobsters. We'll try that. So that's a floating point raster we're going to create. That'll be a floating point. Likewise, where could you generate spending, this final output of a 0 and 1 spending density? Well, that comes back to just what the name would imply here, a raster spending density. Again, that's going to be a floating point. Values like elevation, snowfall, that type of thing. It's going to be dependent upon where the density of points are. Now we can ask ourselves, where could we derive distance to Red Lobster from? And the answer to that one is, well, we have our Red Lobster locations, because we just loaded them and we looked at them, and those we're all dealing with point files, point shape files here. So we have our Red Lobster locations. Likewise, where could we obtain our spending density? Well, we checked out our spending density by looking at our customers. Customers had that attribute in there of our spending density column, so we can obtain that from our customers. So again, this is a point vector shapefile in this case. So what we're going to be doing is just, in this case here, we're going to be deriving data. So here we have our two input point shapefiles. We're going to be deriving a distance raster. We're going to be deriving a density grid or a density raster. Then at this stage, we're going to be doing or implementing here subsetting. Called subsetting, again, whatever you want to use here, or a grid query. At our junctures right here. So subsetting of grid queries. So data derivation. Then subsetting or grid queries to get us down into our final two data layers. Now, once we're done there, we can think about how we want to analyze this, put them together. We could use multiplying. If you want to use that, we could use condition statements. As I mentioned earlier, we'll probably just take you through the condition statement and let you try the others on your own. But we could add these together. That's where breaking these down is helpful, because it allows us to multiply, add, run a condition if we want. And if you're already thinking ahead, and I maybe mentioned earlier, there's a bypass option in here too, where we could sort of say, I'm just going to make a note here, these are variables, kind of our inputs here at the first stage. Variables, which are our data layers, criteria are our metrics for our analysis. But if we're already thinking of the criteria, we do not necessarily need to subset this out if we know it. Instead, we can build a con statement that says, in the condition where this raster is greater than or equal to 5,280, which would be our cell values, and where the spending density is greater than or equal to 0.02, where those are both true, write a 1, where it's not, write a 0. So we're kind of bypassing this step then. But the danger of that is we're sort of eliminating the possibility of doing or implementing other analysis types, such as adding or or multiplication or something like that. So let's keep that in mind. So now that you have that set, let's go ahead and run that. We're going to go through the Red Lobster first, and we're going to create here from our distance toolbox here, we're going to use let's see here, straight line Euclidean distance. I'm just going to pause this, make sure I find the right one for us here before we get going. All right, so we're back and wanted to highlight a brief interruption here, but during the recording, so to take a quick pause here. But one of the appropriate thing where we left off here, we're trying to figure out what is the distance to Red Lobster, and in terms of deriving data, that's where we left off. So I was looking specifically for a straight line distance, your Euclidean distance tool. So you may want to type that in. What this is going to do, it's going to radiate outward from each one of these Red Lobster locations and generate distance values. So with that, let's go ahead and drop in our input raster, which is that of Red Lobster, and our output name here as well. Again, make sure that we have that saved in a good location. So we'll type that in as, I'll call it dist Red Lobster. Dist Red Lobster. And then we'll select save. And our output cell size. I don't know. I mean, you can do this one as 1 if you wanted to. You know, all of our units are in 1 foot. That might be fine. We can try that as 1. Just make sure every other raster that we're generating is that of 1, 2. Now, maximum distance, do not put in here 5,280 feet because we want this to really overlap with everything. And because we're going to query the cell, whatever the cell's values are, that doesn't matter. We'll still subset or query that out. So, okay, this should be okay as it is. We have our Red Lobster points in there, our raster name, output cell size. Let's run it. So it might take a little bit longer to chug just because we have to chug along here because we have our output cell size as smaller. And, so you can set that at 50, you could set it, whatever you wanted to, and that's okay. Well, let's go ahead and, here's another great example that I did not remember to do. So this is a good thing to learn from again, just like we did with the prior activities, that we want to make sure we set our environments appropriately here for that. So I'm going to go ahead and just remove this right away. Here again, it only went to our points. We're going to delete that. I'll remove that, and we'll run this again, and I'm going to call this one just Red Lobster 2. But we'll set the environments this time, our processing extent. We want that to be that of our streets. We'll say our streets. Okay, so our streets. Parameters, and let's go ahead and run that again. So we'll let that run. Might take a little bit to do that. I'll pause this, and when it's ready, I'll be right back with you. Okay, folks, my computer's a little bit older here, and apologize that it was having a hard time chugging along here at the 1 foot cell size. Your computers might be screaming along and done here, but I gave it a few minutes, and mine is a little bit older of a machine here. So what I did was I canceled my operation for the straight line Euclidean distance, and I renamed a new raster to drop in here, dist Red Lobster 3, so 3rd time here, hopefully it'll be good. And I changed my output cell size to 100, and if you have a newer machine, better than mine, yours might cruise along faster, but if yours is processing a little bit slower at the smaller cell size, definitely don't be afraid to cancel that and just rename a new raster, keep everything the same. We'll check our environments again here. We want that same as our streets. And then set your cell size to 100, and let's try that instead. Okay, so it's a little bit faster. It's nice to have the extra detail, but my computer can't handle it here. So here we have a straight line distance outward from all of our Red Lobster locations. And so really at this point, right here, to which now we'll subset out or grid query out all those cells that have a value greater than or equal to 5,280 feet. So let's do that right now, since we're in here. We go down to Raster Calculator. And for my output raster, I will say here that we will give this a name called distance final. Maybe it would be okay. And that'll be a product of our straight line distance. We could say here too, we could use a condition if we wanted, or just a relational operator like we did in one of the prior activities. We'll say greater than. So all stores, any new stores must be greater than or equal to 5,280 feet. And we know that these values are in feet because our original units were in feet. So we'll just type in here 5,280. And again, the default for these sort of quick relational queries, you could write a condition too. That's fine. If you said the condition where the distance raster is greater than or equal to 5,280, comma, or parenthesis, comma, then we could put 1, comma, 0, and then a parenthesis to end those with a condition statement. That's fine too. You can do that either way. Let's run this and extract out our final data set here for distance. So, okay. Like I've been doing already in prior examples, I'm just going to turn off, or not turn off, but no color my 0 values. So we're looking in the green. That's what this means. So the green area is good for our distance final. Now let's come back to our flowchart and let's generate. We're going to drive some data that you can see right here. We're going to drive a spending density floating point layer. Let's do that next. So either you can search for a tool called density, or I believe we'll find it right here in our density tools. Now, a couple of these we may want to try, we'll have to see. I've noticed that there have been different algorithm outputs, and I'm not sure really what exactly is happening. Typically, I've recommended kernel density for giving a little bit more input to some of the weights on our population field, which will be our Z here, which would be spending density. Let's try kernel first. I've noticed that there were some problems with that, but I'm not, maybe it was cleared up since then, but we'll try kernel. Kernel should work. It's always worked in the past, different various versions of, oops, we want customers, various versions of desktop and pro. Spending. So again, our population field always has to be numeric, and we'll call this one here. I'm going to save this as, we'll call this spending. We'll call that spending. We're right here, creating our spending density. Okay. Output cell size, I'm definitely not going to try 1. If yours worked before pretty quickly, you can certainly try 1, or you could try 10 or whatever it is. I'm going to use 100, a 100 meter cell size, just for limitations in my processing speed here. So let's run that. So we have a population spending field here. It's numeric, an output raster called spending, and a cell size of 100. I'm using 100 so that it matches our other straight line distance that we created. Okay. So I'm going to see if I can just check this out here. Now, this is definitely not what is normal on here. So I'm going to, and I don't know why you know, our results should be a little bit larger on here. And I'm not quite sure what is the case with that. Let me try. So this was the kernel. I'm going to remove this. Let's go back in here. This is just kind of what I was talking about. Something is very fishy with that, and it could be in the parameters, how we're setting that up as well. So I might have to look into that a little bit further, but let's try our customers, our population field, here's spending. And it could also be, well, it's not cell size, I don't think, but let's go ahead and try this again. What did we call that here? Called it spending. I'm going to call this spending 2. Output cell size. It might have something to do with our radius or our map units here too. So if we get the same result, my suspicion is that our units type might be, we may want to come back in here and we'll check that later here, but let's give this one a try. So this is the case where units could be really important, you know, like our map units and our projection in here, depending on how the density algorithm is running that based off the points per given unit area. But we'll try this. Okay. This is better, and I'll have to check into this. But my suspicion is there are some issues with either the coordinate system or that project on the fly from the original base map that was defaulted in here that we had to remove. And normally it's a little bit smoother of a situation here, but suppose the other way we could try, I'm just out of curiosity since we're working on this. I mean, if you had a point density that looks like this, we're okay in that. We can definitely use that because we're looking for values of 0.02 or higher. You know, that kind of falls within our band here. But I'm also curious if we try interpolation on this. You know, we could also interpolate instead of creating a density grid. I mean, density is going to cluster our points a little bit more closely together for our areas that we see here, but it'd be interesting. I'm just out of curiosity, I'm just going to try this. You know, interpolation is interpolating the points based off of a value, and I'm just wondering what that will do. I'm also going to try here, we can do an IDW or a spline. I'm just going to run a spline again here. Customers, real briefly. I'm going to call this one, we said spending 3, I'll call it. Cell size 100. I'm going to see if this makes a difference. It didn't in any of those other applications, so that's what's interesting to me. Okay, spending. All right. I've never tried the spline on this before. Nonetheless, maybe the points are possibly too clustered. I don't know. I'd have to look at this a little more. Maybe the cell size was too large as well for the given unit of points in here, which is why a density is a better option to use. Sometimes if you had a cell size of 100 feet, you know, you might have two points within 100 foot cell size, so it may not actually turn out right. But we'll see if 10 feet, a 10-foot cell size, might do the trick here. I don't know. Okay, so definitely interesting. Probably not the best thing to use here, but you can certainly see the range that we have and a lot of the negative values up here that you're seeing. This is a good actually learning opportunity as well to say, you know, where we go beyond our points. You know, we don't have any points way out in these far reaches, and so we have these deep dark pockets. You know, it's sort of trailing off information and trying to predict. And you know, maybe a IDW here would be better to give more weight to the points themselves, or we could set our parameters more or less to the customer limit, as well. But clearly, I just wanted to try that for an idea, but probably not too representative of what we'd want here in this case. So we're going to remove that, and we'll use our point density, knowing that I may want to go back in here and check the actual values, but it's okay for now. I mean, it's not, this is what it generally will look like, but the typical pattern is a little bit more smooth here, so we can see it a little bit more clearly. But anyway, it'll still be fine for what we want to do. So right now we've created our densities spending raster floating point. Now let's subset that out. Subset out our spending density for areas greater than or equal to 0.02. So I'm going to go back here to my raster calculator, and I'm going to say spend final, and we'll call that product of spending 2, where it is greater than or equal to, remember, 0.02. So we're going to go through all of our values here. We're going to pull out all the values, or all the cells that are greater than 0.02. Let's run it. And the defaults again are 1 and 0. Here and again, we could and should, well, this is fine. Just knowing that we're kind of doing a quick version of a con statement in that approach, just for a subset. It's a basic grid query, not a condition statement, just a grid query where the defaults are here. The defaults are in the subset always 1 and 0, but we can use a con statement for that too. So I'm going to mute out my colors, turn off all my spending density, and bring everything up to the top. So my spending density, I'm going to change colors so it's a little bit easier to see. And pick a kind of a dark color. So what we're doing is we're looking for all the areas in red and all the areas in this light green where they overlap. Again, we're looking at an overlay here. So we're looking at really a binary analysis. What we want, or it either meets both of these criteria, in other words, where the cells overlap, or it doesn't, one or the other. And now we could rank this too. If we added our values, we could have a rank, from 2 to 0. In our case here, looking at our 2 inputs, if we like our underneath the green here, we're going to have a 1 here, and the under cells will be 1. So if we added those, this area would be in green here 3. Those would be optimal. Areas out here, like in red, would be a 1, and the green areas in here would be a 1. But all the areas in kind of the white space here, they'd be 0. In other words, they didn't meet any criteria that we had enforced. So let's come back over to our final statement over here. We're going to extract out now in our analysis. We talked about the value of breaking these down into 1s and 0s. Now what will happen, you could try that. Try adding them, try multiplying them if you want to. Adding them will be kind of a ranked or a suitability approach. Multiplying them will be kind of a all in or all out. In a con, we'll get a chance to enforce our parameters here so that we end up with 1 and 0, where the condition where both of these are, test and evaluated for 1, where that's true, right a 1, where it's not, right a 0. So I'm going to come back over here to our solution guide, and we're going to select out the con statement right here. And we'll bring that down in here. And I'm just going to paste that. And it's good. It's good to write those out. And I need to actually make sure that, these rasters are called the same. So just to double check this, I'm going to come in here. I'm just going to say spend final. It's tested and evaluated for 1. And I have a dist final in here too, but I'm just I copied that out. And I want to make sure that we're taking the right rasters here. In con, where spend final is 1 and distance final is 1, where both those are true, right, or 1 and a 0. And we'll call this one then new Red Lobster locations. Let's run it. So we should be just seeing all these areas in green right here. That should appear for us. And that failed, and I'm looking to see where or why that maybe failed. Okay. Condition where spend final is 1 and dist final is tested value. Well, I'm not sure why that's failing. Maybe I'll try a new name. It's going to call it RL. We'll try this, not unless we have any environment set. Okay, extent. That looks okay. All of our spaces look okay. Unless it didn't like. Change the ampersand maybe, but well, we'll try it again. Okay, so something weird is going on here. Oh, let's see here. So maybe you all can figure out what might be happening there. I'm not quite sure. Well, let's write it out by hand then. The condition where spend final tested and evaluated for 1. There was a and where we have our spend final, now distance final. Distance final is tested and evaluated for 1. That's true, we'll write a 1. Where it's false, we'll write a 0. So we'll get our spaces in here. Okay, so all of our parentheses look good. I don't remember if I had a comma. That, no, we did have a comma. Okay, I'm just removing some extra spaces. Our pathway looks okay. We have the correct number of parentheses in here. So let's try it. Okay, so I'm not sure what happened there, everyone. Not really sure. I mean, in theory, it looked like it was the same, or it should have been the same. So, you know, when you're using that code there, you know, if you copy and paste that, just remember that, you know, your names might be different from mine. So it might help, you know, typing that out, you know, before you actually enter that. But anyhow, we turn everything else off. Here we'll be able to see if I mute out my no color and end up with our, oops, streets and our new areas. This is sort of showing all areas that had a higher spending density, given our input consumer points based on their spending, as well as greater than 5,280 feet away from existing store locations. Now, a few things that you could try to do in here is set the map units to feet. You know, we never did that. That could have been a reason why the kernel density didn't work as well, but my suspicion is that it's with the mapping units and or projection, maybe the cell size too, but my guess is with the coordinate system or the mapping units on here, maybe gave it a hard time. But so anyway, that's an application of looking at how we were deriving a new output, which is the whole idea of this: setting a goal, figuring out what your criteria are, and working backwards to find your original parent data sources. even though we had all that, this was hopefully a good exercise in helping you out with that. So with that being said, I wish you all a good rest of the week whenever it is that you review this, and please reach out with any questions. Otherwise, we'll look forward to seeing you all again soon. Thanks for hanging in there.